In this tutorial, we are going to learn how we can control the brightness of an LED using pulse width modulation. And for this, we are going to use an Arduino UNO in order to generate a pulse width modulation signal or a PWM signal using specifically pin number 3 here on the Arduino UNO. So as we can see, what we have is an LED that is connected in series with a 220 ohms resistor, and this resistor is connected to the PWM pin on the Arduino UNO. We will learn about what's a PWM signal, how to write a code in LabVIEW Community Edition in order to control the brightness of the LED using this PWM signal, and how we can have a virtual LED that changes its brightness as well to represent the physical LED. So let us go ahead and check what are the hardware components needed for this tutorial. First of all, we need an Arduino UNO R3, some fixed value resistors, a power source to power up our circuit and Arduino UNO, a breadboard on which we will build our circuit along with some wires, and a USB cable to hook up our Arduino UNO to a PC or a laptop, and finally some colored LEDs. For this specific tutorial, we have chosen a yellow LED compared to tutorial 2. So please refer to tutorial 2 if you want to know more about LEDs, how to hook them correctly to your circuit in order for them to operate properly, and how to size their fixed value resistor. What's a PWM signal? Or what's pulse width modulation? Pulse width modulation reduces the average power delivered by an electrical signal by converting the signal into discrete parts. In other words, we can turn a signal on and off for a certain duration in order to modulate the average power delivered to an electronic component, as we will see in a bit. A PWM signal stays on for a given time and off for a certain time. The percentage of the time for which the signal remains on is known as the duty cycle, as we will see in a bit. If the signal is always on, which means we're taking advantage of the full power that we have, then the signal must have 100% duty cycle, which means it's always on. Now, every PWM signal has a certain frequency, and it's repeated by specifying this frequency, as we will see shortly. So let us go ahead and look at the schematic diagram of a PWM signal to understand it further and to understand the math behind it. So here we have a pulse width modulation signal. As you can see, we have a minimum voltage and a maximum voltage. The minimum voltage, for example, can be 0, and the maximum voltage, for example, can be 5 volts. Now, the on time is when the voltage is set to high, or 5 volts, and the off time is the duration for which the voltage is set to low, or 0 volts. Now, for a PWM signal, it's repeated in cycles, and this is why it has a certain frequency. And the duration of a single cycle right here is known as the period, and the frequency is simply 1 over the period. Now, the duration for which the signal stays on is called the duty. For example, here we have a 50% duty cycle because 50% of the time the signal is on, and for the remaining 50% the signal is off. Now, when we define our signal in terms of time, as we will see shortly, for example, if we have a signal right here that stays on for, let's say, 2 milliseconds, and off for another 3 milliseconds, let's say, then this 2 milliseconds is called the pulse width, which is the duration for which the signal stays on. Now, the duty cycle by definition is the on time over the on time plus off time. And we know that the on time plus off time is the total period of the signal, or the period of one cycle, and the on time is simply the pulse width. And so we have the duty cycle is equal simply to the pulse width over 1 over the frequency. Now, since we have a maximum voltage right here, we need a way to compute our average output voltage depending on the duty cycle that we set. For this case, what we have is V out, which is the output voltage, is simply V max, the maximum value, times the duty cycle. So if the duty cycle is 100%, which means the signal is always on, we'll have V out simply equals to V max. If the duty cycle is 10%, then we'll have V out is 10% of the maximum voltage or the maximum value of the on-time voltage. So let us go ahead and check some examples in order to further understand pulse width modulation, and then we'll move to lab. So first of all, we said that the duty cycle, let's recall the formula, it's equal to the on time over the on time plus off time. And this in turn is equal to the pulse width over period. So let us take a couple of examples in order to further understand it. So let us have a one cycle example for a PWM signal. So let us say that we have here one cycle. And we know that for this one cycle, it has a period right here. So this is our period. And right there we have our pulse widths. And on the x-axis we have the time, and on the y-axis we have the voltage in volts. Perfect. So let us assume that the maximum voltage right here is simply 5 volts and the minimum voltage is 0 volts. So our on time sets the voltage to 5 volts and the off time sets the voltage to 0 volts. And let us take case 1. So in case 1, we'll say we have a duty cycle of 100% or simply a duty cycle of 1. What does it mean, or how do we compute it? So the duty cycle is simply equal to the on time. On time is 100 over the on time plus off time. So it's 100% or 1 over 100% for the on time plus 0% for the off time. And simply we can write it also as 1 over 1 plus 0. And it's simply equal to 1. So our duty cycle is 100%. Now we can also define it in terms of time. In other words, what we are going to say right here is that we have here, let's say a period of, let's say 5 milliseconds for the on time and another 5 milliseconds for the off time. And now I can compute the duty cycle based on such data. Now, if we have 5 milliseconds for the on time and 5 milliseconds for the off time, it means I am at 50% duty cycle because I have half for the on time and half the time for the on time. Now, what about if I have 10 milliseconds? The total 10 milliseconds are for the on time, which is 100% duty cycle. Then we'll have the pulse, which will be simply 10 milliseconds over the period, which will also be 10 milliseconds. So in this case, the period is equal to the pulse width, and this is why we have 100% duty cycle. And simply our V out will be V max, which is 5 volts, times the duty cycle, which is 5, and now we have 5 volts. So in this case, what we are saying is that along the time axis, what we have is a constant value of 5. So we are taking advantage of the full power of our voltage source. Now, what about if we have 50%? Let's take case 2, 50% duty cycle. So duty cycle is equal to 50%. It means in this case, we're dedicating 5 milliseconds to the on time and 5 milliseconds to the off time if we're talking pulse widths and period. Or we can say we are dedicating 50% of the time for the on time and 50% of the time for the off time. So the duty cycle can be 50% for the on time over 50% for the on time plus 50% for the off time, which is also equal to 5 milliseconds for the pulse width over 5 milliseconds for the on time width plus 5 milliseconds for the off time width. And this will give us simply 1 or 5 over 10, which is 0.5 duty cycle or 50% duty cycle. And in this case, our V out will be 5, which is the maximum voltage, times the duty cycle, which is 0.5, and it's 2.5 volts. So we can see right here that using a voltage source that is at 5 volts, I can modulate the on time and off time of the power output in order to deliver half of the voltage or half of the power to my electronic component. And this is a very powerful thing that we can do using a PWM signal. And this is what we are going to do for the LED. If we give it full power, it will be really bright. If we give it half the power, which means 0.5 duty cycle, it will be less bright because the average power delivered to this LED will be much lower. Now let's take one more case, which is case 3, and let's say we have a duty cycle of 10% or simply 0.1. In this case, our on time, let's write it here, on time will be 1 milliseconds and our off time will be 9 milliseconds. So in this case, let's go ahead and compute again the duty cycle to reinforce this concept. So on time, 10% over 50 or 90 for the, or 10% for the on time plus 90% for the off time, it's equal to 1 milliseconds for the on time over 1 milliseconds plus 9 milliseconds for the off time. And logically speaking here, we can see that since the off time is really way higher compared to the on time, we'll have on average a much lower average power. So we'll have 1 over 10, which is 0.1 duty cycle. And in this case, our V out will be V max 5 times 0.1, which is equal to 0.5 volts. And now we can see that we have really a very low average power delivered to our LED, and thus the brightness of the LED will be much lower. So what we are saying here, if you want to look at it graphically, it's as if here I have, because we have 10% of the time the signal is on, and the remaining 90% of the time the signal is. So for 90% of the time, the signal is off, and for 10% of the time, the signal is on. On average, what we will have is a 0.5 volts. So this 0.5 volts right here is the average voltage delivered. So this is graphically. When we had 50% of the time, what we had is graphically 50% of the time the signal is off, and for the remaining 50, it's on, and on average, over time, the signal was at 2.5, so it should be roughly in the middle, so 2.5 volts. And when the signal is always on, or at 100% duty cycle, what we had is a signal, let's throw it in red, a signal that was always on. So the average and the actual voltage are the same. So V out is equal to V max. So here we have 100% duty cycle. Here we have 50% duty cycle. Here we have 10% duty cycle. And if you want to turn off the power or have the full amount of time is at 0 volts, then you will have your voltage equal to 0 over the entire duration. Here we have 0% duty cycle. And we can vary the value of the duty cycle between these two limits of 100% and 0%. So this is it for the theory of the duty cycle and the formulas that we can use in order to really compute the duty cycle, pulse width, speed, or frequency. Let us go ahead now and check which of the pins on the Arduino UNO is a PWM pin and how we can identify it. So if we go back, first of all, this is the schematic diagram for you to replicate the circuit in order to write the code for it. So as we can see, we have the LED connected to the ground, which is the negative side of the LED, and we have the positive side connected in series with the 220 ohms resistor, and this resistor is connected to pin 3 on the Arduino UNO, which is a PWM pin. But how did we know that this is a PWM pin? On the Arduino UNO, a PWM pin is a digital pin, and it's represented by the symbol tilde right here. So we know that a digital pin is a PWM pin or supports PWM signals if next to it we can see the tilde symbol. So as you can see right here, we have the symbol tilde next to pin 3, 5, 6, 9, 10, and 11. And if we go to the actual Arduino UNO, we can read here digital, PWM, and next to it tilde, and we can see the symbol tilde next to pin 3 as well, 5, 6, 9, 10, and 11. So this symbol tells you that this pin or digital pin supports PWM signals. So you should always use these pins if you need to generate a PWM signal. If you try to use other pins that do not support a PWM signal, you will get an error message stating that PWM signals are not supported by this digital pin. Now let us go ahead and build the LabVIEW code in order to control the brightness of our LED. So we will create a VI and we'll place our front panel on one side and our block diagram on the other side. So as usual, what we are going to do is to, first of all, go to Hobbyist, open a connection to the Arduino UNO, get the block to close the connection. And if we go to peripherals right here, last time we used the digital library to get the right block. This time we'll use the PWM library that we can see right here. And inside this library, we have the block for PWM set duty cycle. And this block allows us to control the duty cycle for a specific pin on the Arduino UNO. And this is what we are going to use in order to control the brightness of the LED. Now let us place this block inside a while loop and connect it to the open and the close blocks. Second, let us specify the serial port that we are going to use, which is in this case COM4. And let us look at this set duty cycle block. We can see that it has two input terminals. The first one is the PWM channel that we need to specify, and the second one is the duty cycle, which is between 0 and 1. So for the PWM channel, we know already that it's pin 3, as we said. So if we go back, let's verify it. It's connected to pin 3 on the Arduino UNO, and the sign tilde is next to it, which means it's a PWM pin. Next, we want to set the duty cycle. For that, what we can do, we can have a slider bar in order to change the duty cycle between 0 and 1. So let us here put it between 0 and 1, specify the limits, and let's call it duty cycle 0 to 1. Also, we can call it brightness because it will change the brightness 0 to 100%. Perfect. Now, if you want to make sure that these two limits are respected, the 0 and 1, what we can do, we can go to the properties, to the data entry, uncheck the use default limits, and for the minimum, we can set it to 1, for the minimum to 0, and the maximum to 1. And whenever any value is entered that is outside these two limits, we can use the caution here option in order to make sure that the value is rounded to the nearest value. And that's it. There you go. Now what we are going to do is to just place it here and connect it to our duty cycle controller, slider controller. One more thing, we need a push button or a stop button for our while loop. So let us place it, hide its label, change its style so it looks more trendy and flat. And in case we have an error, we need to make sure that we stop our code. So for that, we can unbundle the error. We can go to the Boolean, so we need to stop our code either using the stop button or in case there's an error. So whenever there is an error, the status here, Boolean value will be true and the code will be stopped. Now, another thing here that we need to make sure we do is to set the duty cycle to 0 whenever we stop our code. Otherwise, the LED will stay on if the duty cycle is not set to 0 before we exit the while loop. To prevent this issue, we can just have the duty cycle blocked outside as well, and we can set the duty cycle to 0 in order to make sure that our LED is off. And in case we have any error, we can use the general error handler right there. Perfect. And that's it. Let us go ahead and run our code in order to make sure it's running properly. So let us place our LED on one side and our front panel on the other side. So now if we run the code, our duty cycle is 0 and we can see that the LED is off. There is no light. Why? Because the duty cycle is 0, which means the voltage output is 0. And remember, for a digital pin, the voltage is between 0 and 5 volts, which means now we're modulating the voltage between 0 volts and 5 volts since we are using a digital pin on the Arduino UNO. Now, if we start to increase the duty cycle, we can see that the LED turns on, and as you can see, the brightness increases dramatically whenever we go to full power. Now notice how the brightness decreases as we decrease the duty cycle and increases as we increase the duty cycle. So let us just magnify the camera a little bit so you can see it clearer. So there you go. Off and then on, and the brightness increases. Perfect. Now, this is it for controlling the brightness of the LED. Now, what about if we wanna have a virtual LED, or if we wanna, let's say, control the brightness in a certain specific manner? So what we are going to do next, I'm going to show you how we can change the brightness in a sinusoidal way or in a step fashion way, like on, off, using the express simulate signal VI. So first of all, let us delete the connection right here, and let us here go to express input and choose the simulate signal block. Now for this simulate signal block, we can have here a sine wave, a square wave, a triangular wave, a sawtooth wave, or simply a DC signal type. Now, first of all, we'll start with a sine wave. For the amplitude, we'll choose 0.5, and for the offset, we'll also choose 0.5. And as you can see, now the value changes between 0 and 1, and this is what we need for our duty cycle. Now, what we are going to do next, here we have two options for the timing. We have simulate acquisition timing, which is the exact timing that we set here for the frequency, or run as fast as possible. For us, we need to simulate the acquisition timing, and we will choose 1 Hertz for now, which means we will change the amplitude between 0 and 1 in a sinusoidal fashion with a frequency of 1 Hertz. Then I'm gonna press OK. Now the beauty here is of this express VI is that we can change the frequency from outside the block. So we can create a control right here and we can change the frequency. So if we show it right there, we have our frequency and we'll just say it's in Hertz. and we can change its style as well to this numeric value. Now what we are going to do, we are going to minimize our block diagram and run our code. But let's first of all make sure that we connected the sine output or the output of the express VI to the duty cycle input on our duty cycle block. And let's run our code and see what will happen. So as you can see now, the LED brightness is changing in a sinusoidal fashion. Now we can decrease the frequency, it will be much slower, or we can increase the frequency to 2 Hertz. Or we can decrease it again if you need to see it in a slower fashion. So as you can see, this is one way of doing it. Another way of doing it is we can here choose the type to be square wave. So it will change between 0 and 1, on, off, on, off. So 0, 1, 0, 1, 0, 1. And we can change the frequency. And once you have the signal type set to square, you will see one more option here, which is the duty cycle. And we can choose this duty cycle ourselves. So let us go ahead and try what will happen right here. So we'll set the frequency to 1. Let us run our code. But before that, let us change the style right here. Replace with NXG silver. And let's align these to have a neat code. So let us run the code. Now we have a frequency of 1 Hertz. Okay. And I can change the duty cycle. For example, if you want 70% of the time for it to be on and 0.25 or 25% of it to be off, you can do that. And we have done that in tutorial 2 in a slightly different way. So please refer to tutorial 2 for more information. And here I can change the frequency. So if we set it to 10 for the duty cycle, we can say 10% of the time it's on and 90% of the time it's off for a frequency of 1 Hertz. We can change the frequency to 0.5 with the same duty cycle. And this is really pretty handy if you want to control your LED in a certain fashion. Now, what about if we want to choose between these two options, whether to control it using the simulate signal express block or the duty cycle block? Simply, we can just set this one as view as text in order to make it neater. Perfect. So let us show how we can choose between these two options right here. So these are our options right here. And for that, we can simply delete this Y right here. We can go to comparison and choose the select function. Now this select function is pretty useful. Why? Because in the middle here, its input terminal says it has a Boolean condition. And this Boolean condition can have two values, either true or false. If it's true, we will get at the output of this select block whatever input is connected to the true terminal right here or to the upper terminal. And if the value of this Boolean is false, we will get whatever is wired to the false terminal right there. And for that, we can have two options. We can either have the sine wave, and this is if the signal is true, or if the signal is false, we want to simply have the brightness control using the slider bar. So we can choose between these two options. And for that, we can have a Boolean button. For that, I'm going to the classic and choose the horizontal button. And I'm going to say, if it's false, we will use the slider. And if it's true, we will use the simulate signal VI. And then the user can choose which mode to use. So let's do that. Let us move it a little bit down. Perfect. And let us wire it. And now it is wired. Perfect. And there you have it. And now we can connect it to the duty cycle. Perfect. So what we are going to do now, we are going to run our code. If it's false, I can have my slider bar And if it's on, I can have again my express VI, which you can see right here. It's functioning properly. Perfect. So let us just make it a little bit faster so you can see it. What we are going to do right now is to have a virtual LED that changes its brightness in accordance with the physical LED. So this way we can see the relationship between the virtual and physical world. So whenever the brightness of the physical LED changes, the brightness of the virtual LED will change as well. Perfect. So let us go ahead and start building our code. So let us go back to our block diagram and check what we have there. So first of all, what we need to do is to create an LED, a virtual LED that will represent our physical LED. And let's call this one LED brightness and place it right there. And now there we have it. Now what we are going to do, we are going to place it outside our VI, right click on it, go to property, go to create, property node, and choose here colors 4 in square brackets. Now what does this mean? This property node allows us to change the color of the LED on demand or programmatically inside LabVIEW. So instead of going to the block, the front panel, right clicking there and changing the colors right here or using the tools palette, what we can do, we can programmatically change the color of this LED inside the block diagram as desired. Now, why does it say here 4? 4 because each color in LabVIEW is represented using 4 unsigned 8-byte integers. So, if we go to any data type right here, any controller of a certain data type, we can see here if I go to the representation, we have different data types. And one of them is the unsigned byte. So, integer. And in LabVIEW, we know that the color is representing using 4 of those. Now, why 4? First of all, we need one 8-byte, unsigned 8-byte for the brightness. So we'll write it right here in order for you to keep it in front of you. We need one for the color R. We need one for, so let me call it red, R. One for the color green or G, and one for the color blue or B. And we know that each color is represented by an RGB color code. Now, for the RGB, we need 3. One for the red, one for the green, and one for the blue. And we know that we can compose any color using these 3 different colors or base colors, the R, G, and B. Plus, we need one unit for the brightness in order to control the brightness of such a color. So I can have a color by mixing R, G, and B, and I can set the brightness of this color using the first element. So for that, I'm going to go right here to this node and say here change to right in order to change it programmatically. Now for this node, it needs, if we press Ctrl H and we press on it, it accepts a cluster of 2 elements. And in this cluster, you need to have 2 arrays of 32-bit integers and an array of 4, one for the foreground color and one for the background color. In other words, we need an array that contains elements for the foreground color and elements for the background colors. Now in LabVIEW, unfortunately, we cannot directly control the brightness of a color and the RGB at the same time. What we need to do instead, we need to work around this problem, and what we need to do is to have one color here for the LED that changes between white and black, and we will overlay on top of this color another color which is green, yellow, blue, violet, depending on the color of the LED that we desired. We will overlay them over each other in order to have the final color that we need. So let us walk around this to show you how it's done. So the first thing we're going to do is we're going to build an array of 4 elements. And in this array, we're going to create a constant for the first element. and we're gonna change its type to U8. And for the others, we're gonna go there and go to NXG, create a numeric controller. And for this numeric controller, we're gonna call it color code. And for this color code, I'm gonna right click here, go to the representation and choose U8 as well. Now for this U8, we're gonna have the same color code for R, G, and B in order to change the color between black and white, as we will see in a bit. So there you go. Now here what we have is an appended array of 4 elements, U8. We need to combine these using a U32 element. 32. Remember, when we pressed H here, it's at 32-bit integer. And we can do that by using the typecast. Since I have 4 U8, I can combine them to get a U32. So to do that, we go to the numeric, data manipulation, and typecast right here. Then we connect the typecast to it. We copy this constant, we wire it to the typecast, and I will tell you why in a second, and we change its representation to U32. And then we have at the output here a U32 data type. Now, what does this typecast block do? Simply it takes an input and converts it to whatever output you need by using the defined constant right here. Since for this constant we defined it as U32 for the data type, unsigned long, I will have the same data type at the output here. Now, if we try to wire it directly to our LED, it won't work. Why? Because we have incompatible data types right here, and we need to make sure we have the proper data types. So in order to do that, what we are going to do, we are going to go to the cluster, go to the bundle, and for this bundle, we're gonna have 2 of these. Now, why do we need to have 2? Because remember here, for this to work, it needs 2 elements, one for the foreground and one for the background, 2 32-bit integers. There's one for the foreground and one for the background. And that's why we need to have a cluster of 2, one representing the foreground and one representing the background. Otherwise, you will get an error. Now, simply, what we need to do is to put these into an array and finally wire this array to our LED. And there you have it. Now, let us go ahead and run our code to see what will happen. Now, if we go ahead and run our code, we have a color of black. And if we increase this one, we can see that the color will change from light gray to full white. And now we have a color that changes between white, shades of gray, and full black. And we can overlay it on top of any color that we desired in order to change the brightness. So what we are going to do here, we are going to go to numeric and here choose the framed color box. This color box allows us to choose any color that we desire. Let's start, for example, with yellow box. So this is LED, or let's say set LED color. So let us call it this way. Now I can take this color and I can combine it with this color. Now, how to combine it? It's very simple. I can simply go to the Boolean, choose the AND, take this one and this color, and simply wire it to my cluster. Now, if we go ahead and run it, I can see that I will have yellow, and now the yellow will change from very bright yellow to very, let's put here 0 to black, or let's say 20 or 100 perhaps, to a very dark yellowish color. And this is what we need in order to control the brightness of our LED. And here we can set any color that we desire. For example, if I put 220 right here, we can set it to blue, we can set it to green, we can set it to orange, any color, you name it, depending on the color of your physical LED. Now what we need to do, we need a way to relate the color code right here that we have chosen to the duty cycle. We need to interpolate or map the duty cycle values to the color code that we need. And for that, it's also pretty simple. We can simply go to mathematics, interpolation and extrapolation, and choose here the polynomial interpolation VI. Now for this polynomial interpolation VI, it has three input terminals: the Y values, the X values that I need, and the X value for which I need the interpolation to happen. For us, our X value is the duty cycle, because I need for each duty cycle value to have an interpolated color code value. And since this is the X value, our X value arrays will be the 0 and 1 values, which represent simply the duty cycle, and the Y values will be the limits for the color codes. So let us go ahead and create a constant right here. Let us enlarge this constant. So we need two elements, make it larger. And for the Y, we need it to be, let's say, between 0 and 255. Now I can make it, can align it right here. Now I can copy this array, and I need the same array for the X value, which is my duty cycle, which is between 0 and 1. And finally, I need the X value, which is simply our duty cycle. Now at the output here, I will have the interpolation value, which corresponds to the color code. Now simply, all what I need to do is to delete this value and wire this value to the color code. Now, as you can see, I need a UA data type right here, but I don't have it. So what I need to do, I need to convert the data type here, which is now a double data type. And all what I can do, I can right click on the wire, insert, numeric palette, go to conversion, and here choose the U8. And now I have the conversion automatically done for me, which is great. Now that's all what we need. Now if we try to go there and work around, we can see that if I change the brightness or the duty cycle, the brightness changes of the virtual LED. But the problem here is if I go to 0 duty cycle, I can see a black color, which we really don't need. So in order to overcome this problem, we can simply just increase the lower bound for the color code to 150, for example. So you can experiment with this value, and as you can see, now we have full bright, lighter bright. Let's make it a little bit lower, perhaps 135. See it? So now it looks much better. It looks darker. Now all what we need to do, we need to see if the physical LED maps to the virtual one. So let us minimize it and let us place our code right there, run it, and let us see. Now we have full bright LED. The physical LED is fully bright, and we have the virtual LED as well. If I decrease the brightness, I can see the brightness of the physical and virtual LED. They are all following each other. And this is pretty much it. Perfect. So now we can control the brightness virtually. And here remember that you can change the color. If you have a green LED, you can do the same. If you have a blue LED, red LED, or whatever, the same thing can be done. For us, it's a yellow LED. This is it for this tutorial.